All right, so today we're going to learn about the number e. So you know about the number pi, which is an irrational number. Today we're learning about the number e, which is another irrational number. So it is actually a number. So before we go any farther, I want you to pause the video and follow the directions on the left that are in pink. When you're done, turn the video back on. Okay, so what you've discovered is, I hope, that, and this is how you should have put the equation in, what you've discovered, I hope, is that this function, as it goes from left and right, it goes up rather quickly at the beginning, but then it begins to go pretty slow. So as we trace y along, we see that those y values are not changing very quickly. As a matter of fact, it seems to be stuck at 2.68, and then it's just gradually going up. So e actually comes from this function. Okay, the number that this graph is approaching is e. Okay, so I'm going to put the definition here for the natural base e in. So you want to write this vocabulary definition down. E is an irrational number where this function that we just looked at approaches e as n increases. So it's approaching that number. So from what we looked at on the calculator, e must be a number that's somewhere around 2.69. Just like, pi is a number around, 3.14. It's not exactly 3.1, but it's around there. So we're going to learn a little bit more about it here. It says, if we look at the next box, the natural base e is irrational, like pi, never repeats, never terminates. It is defined as this function, n approaches positive infinity, as this function approaches e. And now I want you to go to your calculator, and you're actually going to find e on your calculator in two places. One of the places is over here on the right. You see above the caret, there's the pi. Well, above the division sign, there is e. So if I hit second, because e is blue, second, I need to get out of the graph first, I'm sorry. So second and quit will get me out of the graph. And then second and the division sign, and it types e in there, and I hit enter, and it gives me an approximate amount for e. So I'm going to actually write that in over here on my blank. E is approximately 2.718281828. Now it looks like it's going to repeat like 18281828, but it doesn't. Okay, so keep that in mind. It doesn't really repeat at all. All right, so usually when we use e, like pi, we round it up to 3.14. E, we usually round off to 2.72, but there are an infinite number of digits for it. So pi is not the only star in the mathematical sky. All right. Another place that you find e, and we will be using this actually quite a bit as we move along, is over here on the left side. You see this ln key, which we'll also be using pretty soon, and above it is e to the x power. So if I want to raise e to a power, I can go second and then ln, and then put my power in there and raise it to that power. Okay? So now if you just want e, it's over here on the right. If you want e to a power, it's on the left. All right. So we're just going to learn that at the beginning here, just like pi, we can treat e just like it's a variable. So e to the 6th power times e to the 3rd power is e to the 9th power. Okay, so that's nothing new and different, just like you learned with the rules of exponents. And they don't want you to, they wanted us to write 6 plus 3 in there, but we know that. So, and then 18e to the 6th over 2e to the 4th. Well, we can divide 2 out of 18 and 2. So then we have 9 in the numerator and 1 in our denominator. E to the 6th divided by e to the 4th. These 4 in the denominator cancel out 4 in the numerator and leave 2. So we have e squared in the numerator and another 1 in the denominator. So that's times 1 times 1. So our answer is 9e squared, because a 1 in the denominator, of course, we don't need. So it's just like if it was x. It's just that it's e. Okay, and then the last one, why don't you pause and see if you can figure it out on your own. Okay, so we just applied the 2 to each factor, so 4 squared is 16, and e to the 3x squared, we just multiply 3x times 2 and get 6x. So that's all old news. We know how to do that stuff. Now we can also use a calculator to evaluate the expression. So we can do e to the negative 2 power. So we're going to use our key over here on the left that's above ln, so second ln. And I just put negative 2 in my exponent. And we know what that does. It puts it into the denominator. And we get a small number, 0.135. And we'll just round it to 3 decimals. So 0.135. And I'm not too worried about what goes in these other blanks, but in case you are, these are the keystrokes, e to the x, and then the negative sign, and then the 2. Okay, and it gives you the parentheses. And then down here we're going to do e to the 0.3 power. So again, second and ln to get e to the x. I'm going to put 0.3 in my exponent, and then enter. And I get 1.35. So the 9 rounds the 4 up to a 5. So 1.35. So there's a big difference between 0.135 and 1.35. And notice these exponents look very different to get numbers that look kind of the same. So here are a few for you to practice on your own. Please pause the video and do those. Okay, so I just used rules of exponents here. And number 1, negative 3 plus 6 is 3 to get e cubed. And number 2, first I squared the 4 and the e cubed to get 16 e to the 6th, and then I simplify for a final answer of 2e. And on 3 and 4 I just used the calculator. Alright, so in the last lesson in the note-taking guide, we learned that we have exponential growth if we have y equals a, and then we're going to have 1 plus r to usually the t power. So what we should have learned from that is its growth if this factor here becomes bigger than 1. So if that's bigger than 1, we know we have growth. If we have y equals a times the 1 minus r to the t power, then this is going to be a fraction that's less than 1, and we're going to have exponential decay. So this is growth, and this is decay. Well, when we use e, it's going to be a little different. With e, here's what our function looks like. And I know that those boxes are irritating, but I think you can read it on your note-taking guide. Y equals a, it's our beginning amount, times e to the rx power. R is going to be our rate, okay? So now it says if a is greater than 0. That's just a way of saying if a is positive and r is greater than 0. Oh, if r is positive, then the function is an exponential growth function. Then, if a is greater than 0, if a is positive, but our rate is negative, less than 0, then we have a decay function. Now, a can't be negative, okay? Here, they're both positive. The point is, if the exponent, I'm going to write this over here, if the exponent is positive, that's a plus sign, then you have growth. This is only with e. With the other functions, you look for this. Is this factor here bigger than 1, it's growth. If this factor is smaller than 1, it's decay. But with e, if the exponent is positive, it's growth. If the exponent is negative, it's decay. That's only when we have a function with e. By the way, it's called the natural base because it occurs so often in nature. For example, if we were to have written a function for your growth from infancy, e would be involved. The growth of plants, e is involved. So it's very, very common in nature. Okay, so natural base functions. First we're going to look at a, and it says, and we see the equation, y equals 2e to the 0.06x power. And because a here is 2, which is positive, I'm just going to put a plus sign, and r is 0.6, which is also positive, the function has to be, I hope you're thinking it, growth. Okay, so to graph this, we plot the points again for 0 and 1. So y equals 2e to the 0.6 times 0 power, which gives us y equals 2 times e to the 0 power, and we know that that's 1 no matter what the base is. Anything to the 0 power is 1, so y equals 2. When x is 0, y is 2. I'll plot it over here. And then we have